Okay, well, thank you, Chris, for that great introduction in terms of photoperiodic lighting. My name is Roberto Lopez, and I'm a floriculture extension specialist at Michigan State University. And in this part of the presentation, I'm going to talk to you about ornamental photoperiodic studies as well as plant responses. So we're first going to start off talking about light quality. So light quality is basically the relative number of photons, so basically photons of light that can consist of blue, green, red, and far red light. So those are really the light quality that we're going to talk about today, and those other portions of the light spectrum. The wavelength is basically the distance between those waves and different colors. So one unit that we use often with light quality is a wavelength of nanometers, or billionths of a meter. So let's take a closer look, as we can see in this figure. So in terms of photosynthetically active radiation that affects photosynthesis, we're really concerned with 400 to 700 nanometers. But when we talk about flowering, we're really concerned with the red and far red regions, as Chris mentioned earlier today. So phytochrome is a major photoreceptor of plants, and it's really responsible for light detection. It consists of two forms, PR as well as PFR, which have peak absorptions in the red region at 670 nanometers and far red light at 730 nanometers. These control plant morphology in response to those changes in that red to far red ratio. So that's why, again, that red to far red ratio is very important. It can affect, obviously, our photoperiodic responses, stem elongation, as Chris talked about earlier, flowering, dormancy, as well as tuber formation. So again, we see our peak wavelengths of red right around 660 and far red right around 730. So in darkness, phytochrome basically is converted from PFR, right? PFR, we have darkness, it's converted slowly to PR. So let's take a look at short day plants, for example. So as Chris mentioned, short day plants flower when the night length is long. In the day, PR is slowly converted to PFR. The conversion only requires a brief exposure to either white or red light. Now this is really important. As we go on, I'll talk a little bit more about this. So in the dark, PFR is slowly converted back again to that PR. A long night means that there's a long time for that conversion to occur. Under short day conditions, or a long night, at the end of the night period, the concentration of PFR is low. So in short day plants, a low PFR concentration is basically the trigger for flowering. And here we have an example of a crop. So here we have Pennisetum. And again, would this be an obligate or a facultative response? Well, as Chris showed us, we can see these two plants, and we can see that this is an obligate short day plant. Now let's talk about long day plants. So long day plants flower when the night length is short. So in the day, again, PR is converted to PFR. So during a long night or a shortened dark period, PFR does not have time to break down in the dark. Consequently, there remains a high concentration of PFR. So exposure to light during a long night, so either day extension lighting or night interruption lighting, basically prevents that conversion from PFR to PR, thus triggering a flowering response in a long day plant. So for long day plants, they require a high concentration of PFR to trigger that flowering response. So here we have an example of an obligate long day plant. So in this example, it's Coreopsis, so that we can see that under short days, basically we have no flowering, but under long days, the Coreopsis is in flower. So again, let's just review phytochrome again, so that we can see that in short day plants, when we have a low PFR or a long night, we have a flowering response. Now in long day plants, we have to have a high level of PFR or a short night to have a flowering response. Okay, now let's move on and talk about light quality as it's influenced by various light sources. So Chris did a nice job of talking about the various light sources that are available on the market and that we typically use in the horticultural industry. So here we can see in terms of cool white fluorescent lamps, high pressure sodium, incandescent, metal halide, and a flowering lamp. This is one that's made by Philips Lighting. We can see that with the cool white fluorescent lamp, it has a red to far red ratio of 10.7. So what does this mean? Basically, it means when we look here, we have a higher amount of red light compared to far red light. Now let's move on to the high pressure sodium lamp. Again, we see that it has a red to far red ratio of 6, so a higher amount of red light. Now, as Chris mentioned, the incandescent lamp, which has been traditionally used for photoperiodic lighting, has a red to far red ratio of 0.7. Metal halides, red to far red ratio of 3, so we see higher amount of red light. And then we have the newer introductions of an LED, so in this instance, a Philips flowering lamp. And again, our red to far red ratio is 0.8. Now, if you're ever wondering about the sun, in terms of the sunlight, we can see that we have nearly identical light quality in terms of blue, green, red, and far red light. So we have a red to far red ratio of about 1 to 1.1. So here's a nice photograph shared by one of my colleagues here at Michigan State University, looking at the influence of light quality on long day plants. So in this example, again, Coreopsis, which is a long day plant. And here we have a cool white fluorescent lamp, a high pressure sodium lamp, an incandescent lamp, and a metal halide lamp. So basically, these lights provided 1 micromole per meter squared per second of light. And what do we see? Well, as we would expect, incandescent lamps provide a higher percentage of far red light, so obviously we see more stretch. We also see that with Coreopsis, we have flowering with all of the other lamp types. However, with metal halide, we see that we only basically see 1 flower. So again, we can see the effects of various lamps on flowering. And again, these responses vary by species as well as by cultivar. So let's now look into red to far red ratio and how it affects flowering. So here we have a study that was conducted by William Meng and Eric Runkle here at Michigan State. And what we're looking at is basically the percent of red light in red to far red lamps. So here we have long day plants. So we have petunia all the way down to fuchsia, and we have examples of short day plants such as mums, marigold, and dahlia. And what do we see? We basically see that in order to induce long day plants into flower, and in order to keep short day plants vegetative, we need to have anywhere from, let's say, 37 to 52% red light in these lamps. So to visually see this in terms of a flowering response with a long day plant, here we have snapdragon that was grown with red to far red ratios of 140 all the way down to 0.1. So if you remember, I told you that the red to far red ratio of an incandescent bulb is right around 0.7. So here again. So in terms of a flowering response, we see that with snapdragons, we see a flowering response anywhere from 1.1 all the way down to 0.3. Here's yet another example. So in this example, we're looking at 2 long day species. We have petunia as well as ageratum. As Chris mentioned before, photoperiodic lighting is low intensity. So here, they're providing 4 hours of a night interruption at 2 micromoles. The plants were either grown under a 9-hour short day, so as we would expect for a long day plant, those plants are vegetative. Then the plants were grown under 4-hour night interruption, providing 2 micromoles from an incandescent lamp. As we would expect, the plants are in flower. Now here, we find an LED that is just providing red and white light. Now we can see with petunia, which is a far red sensitive crop, the plant is vegetative. We see a little bit more growth compared to under short days, but we don't see any flowers. Now with ageratum, which is far red neutral, we see that the plants are in flower. Now, here's an LED that provides red as well as far red light. And as we would expect, very similar red to far red ratio as the incandescent bulb. We see flowering in the far red sensitive crop and then the far red neutral crop. What about short day plants? How do short day plants respond in terms of that red to far red ratio? So under short days, chrysanthemum is in flower. Under incandescent bulbs, we see that if we're providing 2 hours, or excuse me, 2 micromoles for a 4-hour night interruption, the plants are vegetative. Under red light, we see that the plants are vegetative, as well as under red plus far red light. What other things do we notice? When we provide far red light under incandescence or under a red plus far red LED, we have a little more stem elongation. Here's just yet another example. So here we have a short day plant. This is a bloodleaf plant, which is primarily grown for its foliage, so we want to keep it vegetative. So in this study, we basically grew the plants under a wide range of photoperiods ranging from 9 hours all the way up to 16 hours. We wanted to, again, determine that critical photoperiod in terms of flowering, or a 9-hour photoperiod with a 4-hour night interruption. And what do we see? We basically see that the critical photoperiod for bloodleaf plant is 13 hours. So in order to keep this plant vegetative, we want to grow it under a photoperiod greater than 14 hours or under a night interruption photoperiod. Again, remember, this is a short day plant. So we don't necessarily need that far red light. We can just provide red light. As we can see in this example, by providing red light during a night interruption, again, the plants are vegetative. But more importantly, we also see that that stem elongation is drastically reduced compared to when we have far red light in that lamp. So what are some of the take-home messages in terms of the red to far red ratio? Well, with long day plants, red light can regulate flowering of some crops, and unfortunately, not all crops. So some species, such as petunias, especially the wave petunias, they're going to require that inclusion of far red light. So again, the inclusion of far red light can promote flowering of other crops. So LEDs that have both red and far red light are similar to incandescent lamps because they have a similar red to far red ratio. Now for short day plants, red light alone is effective at inhibiting flowering, and you can prevent some of that unwanted stem elongation from far red light. So now let's move on and look at the promotion of flowering from far red radiation and how it depends on the photosynthetic daily light integral. So those of you who may not be familiar with the daily light integral, basically daily light integral is the cumulative amount of photosynthetic light that a plant receives over the course of a day. So unlike photoperiodic lighting, photosynthetic lighting is much higher intensity, and that's going to affect overall growth. So in this study, we basically grew long day plants. So in this example, we have petunia. And we grew this petunia crop under a relatively low daily light integral of about 7.5 moles. So the daily light integral that we would expect right around this time of the year in a northern latitude. So let's look at this slightly complicated figure. So we have photoperiods ranging from 10, 13, or 16 hours, either provided by lamps providing red and far red light or red light alone. So again, we know that petunia is a short day plant. So when we grow it under a 10-hour photoperiod, for this particular cultivar, we see that flowering is delayed. It will eventually flower. So this is a facultative long day plant. Under a 13-hour photoperiod, when we have red and far red light, we see that the plants flowered in 35 days. Under a 16-hour photoperiod, the plants flowered 3 days faster. However, when we provided the photoperiod with red light alone, we see a very large delay in flowering, no matter if the photoperiod was 10 hours or 16 hours. Now, let's move on and look at a high daily light integral. So in this treatment, the daily light integral was 17.5 moles of light. So the light that we would experience in a greenhouse during late April, early May, especially in a northern latitude. So here, again, a high daily light integral and the same lamps. So red and far red light or red light alone. Under short days, we can see that the plants eventually flowered after 29 days. Under a 13-hour photoperiod and 16-hour photoperiod, when we had red and far red light, plants were already in flower. And we can also see that when we provided just red light alone under either short days or under long days, plants were in flower. So what does this tell us? Basically, if you're in an area with high daily light integral, you're not necessarily going to need that inclusion of far red light. However, if you're in a northern latitude where you're going to be growing your plants under a low daily light integral, it's going to be very important for you to have a lamp that has both red and far red light for long day plants. So now let's move on and look at the effects of blue light. Until the advent of LEDs and the use of LEDs, we really hadn't done any sort of studies to determine if blue light could influence flowering. So in this example, we have 2 long day plants. We have, again, Coreopsis and we have Petunia. So the plants were grown under short days, or they were grown under those LEDs, again, that are providing red and far red light at 2 micromoles. So as we would expect, the plants are in flower. Now, here we're looking at providing a 4-hour night interruption from blue light. So again, we were using LEDs, and we're providing much higher intensities than we would with a red and far red lamp. So here we're looking at intensities from 5, 15, or 30 micromoles of light. And what we have found is when you provide at least, and it's very species dependent, but for Coreopsis, 30 micromoles of blue light will trigger a flowering response. Now with Petunia, we found that 15 to 30 micromoles of light was effective. So what does this tell us? Well, unfortunately, 2 micromoles of light which is obviously low intensity, is ineffective for most long day plants. However, a moderate intensity of blue light of around 30 micromoles is effective. Now let's move on and look at green light. So again, in this study, William looked at varying intensities of green light and compared it to our typical red, white, and far red LED. So again, we have a long day plant and a short day plant. So Ageratum is our long day plant. So under short days, they're vegetative, and under short days, Marigold is flowering. So William found that when you have low intensity green light, you can actually have very similar responses to providing red and far red light. Unfortunately, this isn't the case for every species, as he found with Petunia. So we see that with Petunia, green light, the brighter, the better. So again, when we had 13 to 25 micromoles, we had similar flowering responses to low intensity red and far red light, but very little flowering under a low intensity of 2 micromoles. So what are the conclusions with green light? Under low intensity, for example, 2 micromoles, it's effective on some crops, but not all. 25 micromoles, which is more of a moderate intensity, is effective for most crops. And now let's move on and talk about white light. So white light, again, these are lamps that you could go to a hardware store or a big box store and purchase them. So typically a cool white or a warm white lamp or LED. So in this study, we looked at short days providing red light alone, or red and blue light together, cool white, warm white, or again, the lamp that we've talked about throughout this presentation, red plus far red light, all at 2 micromoles. So here we see that white light can be effective. It's very comparable to our red plus far red lamps, and also we see that the plants are more compact. We also see that providing red light alone or red light with blue light are also effective. But of course, there's always exceptions. So it was moderately effective with other species such as Coreopsis. You don't necessarily have the same flowering responses as you do with the red and far red LEDs. And white LEDs are very effective at keeping short day plants such as mums vegetative. So again, we can see that the plants are vegetative, similar to providing red light alone. Now here, we see that when we provided mums with red plus far red light, they're flowering. So again, with short day plants, red light is much more important. So what's the summary or results in terms of white light? For long day plants, it's similar to providing red light alone or blue plus red light. It's less effective than red plus far red light for some far red sensitive crops. For short day plants, it's effective at inhibiting flowers. So if you were to go out to a hardware store and purchase white LEDs, they would be effective for for short day plants. Now here's a summary, basically looking at the effective lamp types at controlling flowering. So as Chris mentioned, incandescent or halogen lamps are effective for both short day as well as long day plants. Now one of the problems is that these lamps have been phased out of production. However, you still can find them. It's going to be a little bit more difficult. Now those fluorescent lamps, such as the compact fluorescents, they're effective on keeping short day plants vegetative. However, they're not necessarily as effective at inducing flowering of all long day plants. The high pressure sodiums or the high intensity discharge lamps, again, are very effective with short day plants as well as with long day plants. And then when we look at low intensity LEDs, we can see that red lights alone is effective for short day plants, but not necessarily effective for all long day plants. And I'm not going to read through the rest of the list, but again, I've given you those examples and you have them in your handouts. So if you want more information in terms of lighting, you can visit our website here at Michigan State, which is www.floor.hort.msu.edu/lighting. And here we have articles that we've written in the various trade magazines as well as bulletins on photosynthetic and photoperiodic lighting. I'd also like to mention a book that Chris, Neil, and I were authors. This is a book that came out in 2017. It's a 18-chapter book on a wide variety of topics, including photoperiodic lighting, and it is available on Amazon. And with that, I'd like to thank our sponsors for today's webinar, PL Lighting, and I could entertain any questions you may have at this time.